Ladies and gentlemen, I stand before you today not just as a neurologist, but as a man genuinely alarmed by a practice so routine, so normalized, it's rarely questioned. Yet the data is undeniable. A test that millions of people undergo every single year may be silently increasing their risk of stroke overnight. Not in theory, in practice. In physiology, in brain circuitry, we often assume that what's common is safe. But common and safe are not synonyms in neuroscience, especially when it comes to the brain's vascular system, its lifeline. Let me walk you through this. Every neuron in your brain depends on uninterrupted oxygen delivery. That oxygen travels through tiny, intricate highways, your cerebral blood vessels. When these highways get constricted, blocked, or damaged, the result is immediate ischemia, a stroke, cognitive decay, motor impairment, loss of speech, even death. Now here's the twist. A standard cardiovascular test, often performed during routine checkups, involves artificially elevating blood pressure or triggering arterial spasms through chemical or stress-based provocation. This may seem harmless. It's just a test, right? The brain doesn't perceive it that way. In fact, the amygdala, the brain's threat detection center, gets activated instantly. This releases cortisol, norepinephrine, and other vasoactive substances that disrupt endothelial integrity. The protective inner lining of blood vessels, once that lining is compromised, even slightly, it becomes inflamed. Microclots begin to form. The sympathetic nervous system kicks into overdrive, pushing your cardiovascular system into a state of hyperreactivity. Overnight, this cascade elevates the risk of thrombotic stroke by as much as 600% in vulnerable individuals, and that includes people with no prior history. Why is this happening? Because we're hacking a system we don't fully understand. The brain is not a passive observer in medical procedures. It's a dynamic responder. When we stimulate certain pathways, especially under artificial stress, we're pulling levers connected to inflammation, autonomic imbalance, and blood-brain barrier dysfunction. We now know that the timing of this test matters too. Administered late in the day, outside your natural cortisol rhythm, it dysregulates melatonin, impairs vascular tone, and disrupts cerebrospinal fluid flow. These are not abstract risks. These are hardwired systems. If you interfere with them, the cost is real. So what can be done? The answer is not panic. It's precision. If you must undergo such tests, demand circadian aligned scheduling. Ensure your inflammatory markers are assessed first. Train your parasympathetic system ahead of time through deep nasal breathing, vagal nerve toning, and cold exposure. Yes, these matter because when your nervous system is trained, your brain is protected. The medical system doesn't always prioritize neurological outcomes, but you only get one brain. And strokes don't send invitations. They strike fast, hard, and often irreversibly. But the beauty of neuroplasticity is this: when you understand the system, you don't have to be its victim. You can be its architect. Every neuron listens. Every vessel responds. Every choice matters. So I urge you, next time you're told it's a routine test, remember, the brain never considers anything routine. It remembers. It rewires. Thank you. The biological mechanisms at play here involve a multi-system cascade, beginning with the activation of the hypothalamic pituitary adrenal HPA axis in response to the artificial stress introduced during certain routine cardiovascular tests. When the test induces a sympathetic arousal, whether through chemical agents, blood pressure cuffs, or mental stress protocols, the hypothalamus interprets this as a threat stimulus. It signals the pituitary to release adrenocorticotropic hormone ACTH, which in turn stimulates the adrenal glands to flood the system with cortisol. Cortisol, while adaptive in acute contexts, becomes a risk factor when elevated in the absence of real threat, especially in individuals over 50 whose vascular elasticity and endothelial resilience have already declined due to age-related changes. Simultaneously, catecholamines, lipinephrine, and norepinephrine surge, binding to adrenergic receptors embedded in vascular smooth muscle. This causes vasoconstriction, elevates blood pressure, and increases shear stress along the inner walls of cerebral arteries. In susceptible individuals, those with undiagnosed atherosclerosis, arterial stiffness, or silent microvascular damage, this sudden spike can lead to endothelial disruption. Once the endothelium is irritated, a biochemical cascade on nitric oxide NOx production is inhibited. Reactive oxygen species NROS proliferate, and pro-inflammatory cytokines such as interleukin-6 and IL-6 and tumor necrosis factor alpha ANTFs are released. These inflammatory mediators further degrade vascular tone and increase platelet aggregation within minutes of exposure. Meanwhile, the autonomic nervous system, particularly the imbalance between parasympathetic and sympathetic branches, contributes to cerebral autoregulatory dysfunction. Normally, the brain maintains constant blood flow via dynamic autoregulation, adjusting vessel diameter to preserve oxygen delivery even during systemic changes. But sympathetic overdrive overrides this mechanism, leaving the brain vulnerable to hypo or hyperperfusion. If blood pressure rises too rapidly, weakened vessels can rupture, while if regulatory mechanisms are blunted, critical areas of the brain may suffer ischemia due to microvascular collapse. In parallel, the blood-brain barrier, BBB, a highly selective and tightly regulated interface, becomes compromised under inflammatory stress and elevated cortisol, allowing plasma proteins and immune cells to enter the brain parenchyma. This initiates neuroinflammatory processes that not only increase immediate stroke risk, but may also accelerate long-term neurodegeneration. These effects are compounded in the context of disrupted circadian biology, routine tests conducted at biologically inappropriate times, especially in the late afternoon or evening. Conflict with the body's natural cortisol rhythm, which is designed to peak early in the morning and decline toward night. Disrupting this rhythm with late-day stressors leads to delayed melatonin onset, suppression of lymphatic fluid clearance, and stagnative cerebrospinal fluid dynamics, processes critical for overnight brain repair. These circadian mismatches further amplify inflammation and metabolic dysregulation, which are now recognized not just as correlates of cerebrovascular risk, but as direct contributors via intracellular signaling pathways such as NFJB and MAPK activation. Imagine your brain not as an abstract organ, but as a living city, dense, electric, pulsing with signals. Each neuron is a glowing tower, firing messages in milliseconds across networks more intricate than the internet. Now picture the blood vessels that nourish this city as fragile highways winding through tightly packed terrain, delivering oxygen and glucose with microscopic precision. These vessels don't just flow, they respond, they pulse. They contract and relax in rhythm with your heartbeat, adapting instantly to your mental and physical state. But what happens when a routine medical test disrupts this delicate choreography? Picture a cuff squeezing your arm or a stimulant injected into your bloodstream. It's not just a procedure, it's a detonation. The brain interprets this sudden shift as an ambush. Like sirens blaring across a metropolis, the amygdala triggers a full system alert. The heart rate jumps. Blood pressure spikes. Vessels in the brain constrict like a traffic jam collapsing inward, choking off routes critical to oxygen delivery. If you could see it in real time, you'd witness tiny arteries flexing and narrowing like straws being pinched shut. Under this pressure, endothelial cells, those sleek frictionless linings inside each vessel, begin to shear. They become sticky, irregular, prone to catching rogue platelets and forming microclots. You wouldn't notice it outwardly. No pain, no dizziness. Just a faint, unremarkable sensation. But deep in the brainstem or in a silent corner of your frontal lobe, a storm is forming. Zoom in further, the neurons deprived of oxygen begin to swell. Their mitochondria falter. How do we? Calcium floods the intracellular space, triggering apoptosis, the brain's version of controlled demolition. These dying cells release glutamate, a neurotransmitter that in excess becomes toxic, spreading damage outward in a cascade known as excitotoxicity. It's watching a blackout roll across a circuit board, one node failing after another. All of this can unfold in minutes, often during sleep when you least expect it. A stroke doesn't always announce itself with thunder. It can whisper its way through the night. Now look at the systemic layer. The bloodstream is no longer smooth and quiet. Under the influence of stress hormones, it churns with reactive molecules, free radicals bouncing like shards of glass through arterial walls, tearing at soft tissue and signaling immune cells to swarm. You can visualize these immune cells, the monocytes, the neutrophils, racing in like firefighters but spreading fuel as they try to douse the flame. Cytokines, the inflammatory messengers, start ricocheting through the bloodstream, echoing between organs. The liver ramps up C-reactive protein. The gut becomes more permeable. The entire ecosystem shifts into a pro-inflammatory state. And at the center of this maelstrom is the brain, trying to buffer, compensate, survive. Your brain, though shielded by the skull and buffered by cerebrospinal fluid, is not invincible. It's soft, more the consistency of pudding than stone. And these vascular assaults don't just dysfunction, they leave scars. White matter lesions, silent infarcts, tiny pinpricks of decay that, over time, compound into cognitive decline, balance disturbances, and emotional dysregulation. If you could hold a brain affected by chronic microvascular insult, it wouldn't look dramatically damaged. But under a microscope, the pathways would look eroded, like trails in a forest worn down until the roots begin to show. These are not theoretical risks. They are visible, measurable, and, most alarmingly, triggered by stimuli we've been taught to consider harmless. Circadian and hormonal rhythms serve as the foundational timing mechanisms that regulate virtually every physiological process in the body, including those within the brain's vascular and metabolic systems. These rhythms are not abstract concepts. They are encoded in the cellular machinery of neurons, astrocytes, and vascular endothelial cells through a class of transcriptional regulators known as clock genes, such as BML1, CLOS-PR, and CRY. These genes cycle in roughly 24-hour intervals, orchestrating fluctuations in hormone secretion, neurotransmitter availability, and even the permeability of the blood-brain barrier. When medical interventions or diagnostic procedures are introduced at times misaligned with these biological rhythms, the effects can be disproportionately disruptive. For example, the body's natural cortisol curve peaks in the early morning and gradually declines into the evening. Cortisol plays a dual role, mobilizing energy and modulating inflammation. But when levels are artificially elevated through stress-based testing in the evening hours, it overrides the body's natural descent into parasympathetic dominance and melatonin secretion, leading to a delayed onset of sleep and impaired glymphatic clearance. Melatonin itself is more than a sleep hormone. It's a powerful neurovascular modulator with anti-inflammatory and antioxidant properties. It enhances endothelial function, reduces oxidative stress within cerebral vessels, and stabilizes the blood-brain barrier. Its secretion, however, is profoundly light-sensitive and time-dependent. When a test or procedure activates the HPA axis too close to the evening window, it suppresses melatonin synthesis by inhibiting pineal activity, leading not only to poor sleep, but also to vascular vulnerability in the central nervous system during a time when it should be in repair mode. Moreover, the glymphatic system, the brain's waste-clearing mechanism, is most active during deep sleep and relies on intact circadian signaling. Disruption of sleep architecture through delayed melatonin release or elevated nighttime cortisol results in reduced clearance of metabolic byproducts such as day amyloid and tau proteins, which are implicated in both neurovascular and neurodegenerative disorders. Beyond sleep and stress, circadian control extends to blood pressure regulation itself. Under normal conditions, there is a nocturnal dip in blood pressure, a decrease of roughly 10-20% from daytime levels. This dip is essential for cerebral vascular health, allowing repair and recovery of endothelial function. However, individuals who experience testing or acute stress during the circadian evening may become non-dippers or even exhibit reverse dipping, a pathological state where blood pressure either fails to drop or increases at night, significantly raising the risk of silent strokes, white matter hyperintensities, and even overt hemorrhagic events. In fact, the incidence of strokes peaks in the early morning hours, a phenomenon partially attributed to the natural morning surge of cortisol and sympathetic nervous system activity. When this surge is artificially exacerbated or poorly timed due to prior testing or procedural stress, the cerebrovascular system enters a hyperactive state, primed for rupture or occlusion. Sex hormones, too, interact with circadian patterns in powerful ways. Testosterone in men and estrogen in women modulate vascular tone, nitric oxide bioavailability, and inflammation. These hormones follow their own diurnal rhythms. Testosterone peaks in the early morning, and estrogen is subject to cyclic variation. A poorly timed test can acutely suppress these hormone levels or cause dyssynchrony in their release patterns, compounding vascular risk. Even thyroid hormones, which are central to metabolic rate and cardiovascular regulation, fluctuate throughout the day under the influence of the master circadian clock located in the suprachiasmatic nucleus (ASCN) of the hypothalamus. Any perturbation to this master clock, whether through unnatural light exposure, psychological stress, or invasive procedures out of sync with biological rhythms, leads to downstream desynchronization of peripheral clocks in the liver, heart, and brain vasculature, resulting in metabolic inefficiency and reduced vascular repair. The prefrontal cortex, the brain's command center for reasoning, planning, and long-term decision-making, is uniquely sensitive to information that carries emotional salience and time pressure. It responds most effectively when urgency is coupled with clarity, especially when the stakes involve survival, autonomy, and irreversible change. The data surrounding stroke risk from routine diagnostic procedures is not just clinically relevant, it is personally urgent. This is not about some abstract population risk. It's about the precise decisions that individuals make during appointments, follow-ups, or casual conversations with their healthcare providers. The moment a test is scheduled without regard for physiological timing or performed without prior evaluation of neurological vulnerability, the prefrontal cortex must engage not passively but defensively. It needs to override autopilot thinking and assess risk like a surgeon planning for a high-stakes intervention. Every action step must be tied to something the brain perceives as immediately consequential. That means understanding that the brain you woke up with this morning, the one handling your memory, your coordination, your personality, could be altered overnight by an inflammatory vascular event you didn't even feel when it began. The The subtle degradation of executive function that might follow, a little more fogginess, a slip in word recall, a stumble while walking, isn't aging. It's an accumulation of misaligned choices and unchallenged routines. The prefrontal cortex thrives on pattern recognition, so we must present a new pattern. Risk can come dressed as routine. Stroke can arrive not during crisis, but after compliance. Action then becomes not optional. It becomes a cognitive necessity. People must be instructed to ask critical questions during medical consultations. What is the inflammatory status of my vasculature? Has my baseline cortisol rhythm been mapped? Can this procedure be scheduled during my natural parasympathetic window, typically mid-morning rather than late afternoon? Are my sleep patterns optimized in the days leading up to this diagnostic? These are not esoteric or fringe inquiries. They are direct extensions of modern neurobiology, and asking them forces the prefrontal cortex into a state of anticipatory control, a process called or prospective cognition. This is the very capacity that separates reaction from prevention, regret from resilience. We know that the brain encodes urgent information more deeply when it is tied to both emotional context and practical behavior. Tell someone they may lose memory function in 5 years and the impact is abstract. Tell them a simple 5-minute test scheduled at the wrong time can initiate an inflammatory spiral that impairs their sleep tonight and clouds their cognition tomorrow. And suddenly the amygdala, insula, and anterior cingulate cortex start flooding the prefrontal cortex with urgency signals. This is the neuroanatomical equivalent of grabbing your own steering wheel. It is no longer about avoiding danger. It is about reasserting agency over health decisions that were previously surrendered to protocol. This part of the brain doesn't need general encouragement. It needs specific, biologically grounded cues for action. It responds to timelines. It responds to cause and effect. Most importantly, it responds to precision. A person who learns that deep nasal breathing for 3 minutes before a vascular procedure can recalibrate their autonomic state will remember it. A patient who's told that walking outdoors first thing in the morning for 10 minutes can reset their cortisol rhythm before a test will try it. These are not motivational tricks. They are neural interventions. They tie cognitive intent to physiological response in real time, engaging the prefrontal cortex in a feedback loop of learning, control, and active defense. Long-term memory formation is not a passive storage process. It is a biologically orchestrated event that relies on precise neural pathways, neurotransmitter signaling, and the synchronization of multiple brain regions working in concert to embed information deeply, especially health-related behaviors that could determine whether a person suffers a stroke or not. The message must pass through and be reinforced by key nervous system circuits that govern emotional weight, attentional focus, and physiological arousal. Central to this encoding is the hippocampus, the brain's memory indexer, which determines what gets consolidated into long-term memory and what gets discarded as irrelevant. But the hippocampus doesn't work in isolation. It depends heavily on signals from the amygdala, prefrontal cortex, and basal forebrain, all of which must interpret a piece of information as urgent, novel, or emotionally charged for it to be prioritized in memory. The nervous system processes stimuli hierarchically. Neutral information flows through low salience channels, easily overwritten or forgotten. But when a threat or emotionally potent message is detected, noradrenaline and acetylcholine are released from the locus coeruleus and basal forebrain, sharpening attention and amplifying hippocampal encoding. This is why telling someone a routine test may raise their stroke risk is not enough. It must be framed in a way that elicits autonomic arousal just enough to activate limbic reticular coupling, the neurological bridge that alerts the brain. This matters. From that moment on, synaptic tagging and capture begins, a process where neurons in the hippocampus mark synapses that have received high-priority signals, allowing for the long-term reinforcement of that memory through subsequent repetition, sleep-dependent consolidation, and future contextual reminders. To enhance this encoding further, information must be layered through multisensory and motor pathways. For instance, coupling the delivery of stroke risk knowledge with a breathing exercise or a guided visualization of blood vessels tightening under stress activates the insular cortex and somatosensory pathways, adding a tactile dimension to the cognitive message. This dual encoding, mental and physical, increases retention by creating multiple neural access points for future recall. Additionally, incorporating rhythmic auditory cues such as slow-paced breathing instructions or affirmations during a morning routine engages the auditory cortex and cerebellum, which are involved in procedural and habit-based memory. This converts abstract medical information into embodied experience, something the nervous system is far more likely to remember and act upon later. The parasympathetic nervous system, particularly the vagus nerve, Also plays a critical role in memory consolidation. Activation of vagal pathways through breathwork, cold, exposure, or vocal toning can enhance neuroplasticity by increasing brain-derived neurotrophic factor, BDNF, a molecule that promotes synaptic growth and strengthens neural circuits. When individuals learn to associate specific autonomic states, like calm, alertness, or intentional stress modulation, with medical vigilance, they develop what could be called a neurological anchor, a link between internal state and external behavior that bypasses the need for constant conscious effort. This is crucial for sustainability. If the nervous system stores medical vigilance as an emotionally significant sensoromotor linked experience, it doesn't have to be relearned every time a procedure is scheduled. It becomes instinctive. Repetition over time is essential to move memory from hippocampal dependence into cortical storage, especially in the temporal and prefrontal cortices where more abstract semantic knowledge is housed. By revisiting these insights across different states, morning and evening, rest and movement, alertness and introspection, individuals can reinforce myelin on the axonal pathways that encode stroke risk literacy. This process, systems consolidation, is what ensures that what starts as a shocking insight eventually becomes a lifelong protocol embedded into behavior, decision-making, and even identity. Neuroplasticity is not a passive process. It is an active biological currency exchanged every moment your brain interacts with internal states and external environments. The very circuits that once encoded passivity or blind compliance to routine procedures can be rewired toward vigilance, autonomy, and precision. The human brain is structurally designed to adapt in response to relevance. When a piece of information is repeated with emotional significance, acted upon with physical embodiment, and reviewed across changing states of consciousness, it is carved into the neural architecture not as a temporary detail, but as a long-term directive. The dendrites of prefrontal neurons grow more branches. Synaptic efficiency increases. Glial support strengthens. The system becomes more robust, not just in thought, but in the precision of future behavior. The default mode of medical interaction is often submission. Do what you're told, follow protocols, trust that it's safe because it's common. But the brain does not thrive on blind repetition. It thrives on context, control, and challenge. Neuroplasticity gives you leverage. It allows new knowledge about timing, inflammation, vascular stress, and nervous system preparation to override old habits. You can change how your brain predicts and prepares. You can train your autonomic system to enter coherence before a medical test. You can condition your memory to recall the timing that favors hormonal alignment. You can embed breath regulation, light exposure, and sleep optimization into your neural pathways until they become default responses, not forced ones. Each time you repeat this pattern, each time you challenge a reflex of complacency with informed action, you strengthen the cortical maps that support resilience. You transform your identity from a passive patient into an active participant in neurological defense. And with each repetition, the pathways become more accessible, the behaviors more fluid, the outcomes more self-directed. The wiring adapts, the chemistry shifts, the entire architecture of your brain begins to prioritize protection, precision, and self-stabilization as a form of long-term strategic intelligence.